Any questions on that? Good. What I thought would be good to do just quick here is do this example number 6. You've been getting a lot of rain lately. And so the Lake Hartwell, which is right next door to us, has been rising. So, one of the questions would be, when we get a little bit of rain, what effect does that have on the water level? So we can do it just in a simple way, what to expect. And we can do it with the water balance. So the Lake Hartwell drains that many square miles. So that's the drainage watershed, and the area of the lake is 93 square miles. So pretty good sized lake. And then there's a rain that it drops 3 inches over the watershed. 2 inches are intercepted or evaporated, so put back in the atmosphere, but 1 inch reaches the lake. And so how much does the lake level rise as a result of that? We've had a couple of rains lately that have been about 3 inches. So what kind of water level rise do we expect as a result of that? So I don't know, what do you think? Just what's your gut? Like, if you have 1 inch of rain, you have like a 1/4 inch of rise of the lake, or foot, or 10 feet? What do you think? 10 feet? Like this? Okay, seems good. I don't know, that's a lot of water, that's a lot of rise in the lake level, but maybe so. Anybody else have a idea?
So some 21 inches.
Couple, 21 inches would seem a good guess, yeah. All right, so let's just go and set the problem up. So here's what the lake looks like. Here's the lake, and then the watershed is a much larger area. So we have the lake, and then watershed draining into the lake. And we can define the watershed like this. So we can set this up then as 2 regions, the overall watershed and the lake itself. So we can draw the control volume here. One control volume goes around the lake, and that's the area of the lake, and another control volume goes around the watershed. And the watershed is much larger than the lake. So we could, I'm not sure whether that area is including the lake or not. It should be not, but let's just say our second control volume is that, and that's the area of a watershed. So we can do the balance, in equals out plus change of storage, on these 2 areas. So the watershed well, let's finish our problem here. So here's precipitation coming in, and then we've got ET coming in, and we'll assume that's happening to the watershed. And then there'll be also flows from the lake, or from the watershed into the lake, and we'll call that Q. And then let's just say that there's a dam here, so let's say they close the outflow of the dam for a couple of days, and make our life a little bit easier. So we'll get the water level change in the lake as a result of when there's no outflow. So this would be the maximum that you could get. So the basic balance is going to be volume in is the volume out plus the change of volume stored. And so the volume in to the watershed is just the precipitation times the area of the watershed. Volume out will just be Q. And so Q plus the evaporation, ET times the area of the watershed. Okay, so both the precipitation and ET are volumetric fluxes. We have to multiply by area to get them into a volume. I don't know, I use this for a volumetric rate. This isn't really, now let's do this as, instead of Q, let's just call it V out. And I'm gonna change this to V out. Because we don't, this is just gonna be a volume, so we're not really doing this in terms of rates, we're just doing it in terms of volumes.
Wait, so is evapotranspiration times the area of the watershed 0? Because it's V out equals V out plus evapotranspiration times the area.
Yeah, sorry. Let's call it let's call it V O W. The V out of a watershed. V out would just be a generic V out, and this is the volume going out of the watershed by flow into the lake. And then we'll just assume that the change of storage in the watershed is equal to 0. So that's for the watershed, and then for the lake, we'll do the same thing. V in, so we could include what's called direct rainfall, which is the rain that is falling right on the lake. But let's just ignore that for now and just assume that all the water that is coming in is coming from the watershed. So V in to the lake will just be V out from the watershed. V out of the lake, we said the dam was closed. So that will just be equal to 0. And then we have the change in the volume stored. Okay, so that's going to require another sketch. So what I'm going to do is, this is what Lake Hartwell really looks like, but I'm going to draw a simplified version of Lake Hartwell. So there's Lake Hartwell, there's the area of the lake, and this is the volume stored. So this is the average depth of the lake. And when it rains, the water level is going to rise. So that's delta H, the amount that the water level rises. And that region in there is the change in the volume stored from the water level that rises. So that's just going to be equal to the area of the lake times the water level rise. Okay, so we have the components. We can put them in here. For the watershed, we get that PAW. That's the volume that goes in equals the volume that flows out plus EPW. And over here, we get VOW equals M. Okay, so these are the components. And then this is what you get when you substitute it in for the volume. Okay, so we're just really following the script that we said we would do for all these problems. For all the control volume, in and out, and change in storage. So what I'm gonna do is subtract off this from each side. So ET, AW. So it's okay, so I bring that over. And we can factor out AW. Okay, and that equals the volume out. Well, for the lake, they have this balance on the lake. The volume coming in is equal to this change in storage. So we can just set this equal to that. And I'm gonna write that in a color. Wait, let me do this. Now I've got some more space. So I can do AW. Okay, so P minus CT, this is like the net rainfall, right? It's the amount of rain that we have remaining after rainfall and evaporation. So this is the net rain. We said that was 1 inch. So we just solve for the change in the water level. And that's AW over AL times the net rain. So this is the water level change. And this is the net rain, and this is the amplification factor. It amplifies the net rain as a water level. And it's just the ratio of these two areas, which I think it was like 2088 over 93. And that was, what did we say about 21?
I said 21.
21, yeah, it's fine. So that's 21. So you have a 21 to 1 area ratio between the watershed and the lake, and that's how much the water level changes. Okay, so I think it has kind of an intuitive basis once you get through it, but it also follows from this basic water balance concept that we talked about last. Okay, so we're good with that? All right. So what I want to do today is to start looking at how we're going to analyze flow of groundwater. That will be an important theme that we'll look at throughout the course. What we started with here was another important theme, which is the conservation of mass or conservation of volume. And now we want to get into the theme of how to evaluate flow. So we need to have a law that we go with, or we need to have like a concept. And I don't know, what's the concept for flow that we would adopt? Flow's going downhill, and that's kind of a intuitive concept that seemed good. Flow's going downhill. Stuff flows downhill. Flow in equals flow out. Flow, well, flow in equals flow out, yeah, that's the conservation law. So we need to have a law about, well, and actually, the conservation law doesn't really require that there's flow. Just somehow the stuff goes in and somehow it goes out. And we'll apply it to flow, but we want to have another law governing flow.
Darcy's laws?
So we'll get to Darcy's law. That'll be an important law. But we want to just start conceptually. So, in just kind of a common lingo, you would say like water or other stuff flows downhill. So that's from high to low in elevation downhill, right? So water certainly does that, but does it always need to do that? Does it always flow from high elevation to low elevation? Can it only flow from high elevation to low elevation?
Are we talking about flow in the liquid phase?
Yeah. I mean, this would also work for gases, vapors, but let's just stick with liquids for now.
Just high pressure, low pressure.
Okay, so water will flow to from high pressure to low pressure. Yep. Will it flow from low pressure to high pressure? What do you think? I mean, it will flow from high to low. Will it flow from low to high?
I mean, you'd have to add energy to the system to do that, though, right?
Well, yeah. Will it flow from? Can you have it flow from low pressure to high pressure? Let's put that on hold. So water is flowing downhill, and it certainly will do that, and it certainly can flow from high pressure to low pressure. In general, though, the thing that we have to go with is not downhill, because water can flow uphill, no problem, right? Lake Hartwell, if you go down to the bottom of Lake Hartwell, the water that's down there ends up at the surface, right? So you can have water flowing upwards. It's not gonna flow up a slope on its own, but that's a different question. It can flow upwards, so it can flow in any direction. So flowing downwards is not really the thing. When it flows downhill, what it's doing is flowing from high energy to low energy. Okay, so that's the law that we'll go with. That's conservation of energy. So we have a chunk of water, and it flows, and the flow process dissipates energy as friction. So it's going from high energy to low energy. So that'll be the kind of the guiding principle that we'll use to think about flow. So here's the stuff that we want to go over today: hydraulic head, different components, what it all means. So hydraulic head. So water's going to flow high, low. Okay, so that'll be the governing principle that we'll want to do. So we're going to have to characterize the energy that's in water. So we'll do that, and to get started with that, we need to have the units for energy. We'll always use units to check ourselves. So remember what the units of energy is? like the basic units, mass, length, and time.
And mass weight squared over time squared. You remember that?
Cool. All right. So, I don't really remember what it is, but I remember that it's the energy is force times the length. That's what I remember. So force times the length, and force is mass times acceleration, and acceleration is length per time squared. So this is mass times acceleration, which is length over time squared, times another length. So they're the basic units. So that's what we're going to be using when we put together these different components. And the different types of energy that we can have water or have in water would be, remember from physics, we've got what different kinds of energy.
Potential, thermal.
Potential. Yep.
Kinetic.
Kinetic. Yeah. Did you say thermal?
Yes.
Yeah, we're not going to include that. We're going to assume we're not going to include that here.
Internal energy,
And then another form,
internal.
internal. Okay, so the way that it'll be, we'll represent that is with pressure. So those are the different forms of energy that we're going to consider now. And so here's the way that we'll go about doing this. We're going to say that there's a block of, take just a unit of a cube, a unit volume. And this is potential energy. So take that unit volume. And so elevation potential energy is going to be measured relative to a datum. So we establish a datum. And then the elevation potential energy of that thing would be, we have to have units of, well, we'll check the units. So it's going to be mass times elevation, or times g times elevation, right? So mass times acceleration is a force, and then the elevation gives us energy. So we want to have the potential energy of that thing. It's a cube, we have a volume. So we'll say that the density is mass per volume. So we can replace mass with density and volume. So this. And then so rho and G end up showing up together a lot. So we'll group them together. That's the gamut of the unit weight. So it's like the weight per unit volume. So weight is a force. So this has units of, force per volume. And you can also write that like this: force per area per length. So force per area, we'll see in a slide or two, force per area is a pressure. So unit weight can be expressed as like pounds per cubic foot or as a pressure per unit length. Okay, those will be useful ways of representing. So let's see, we can, well, let's do this. Let's do the units of the unit weight. So this is gonna have basic units of, well, force per volume. So force is mass, length, volume. Okay, those are the basic units. So, right, control energy, those two combined. Yeah. Okay, so that's the elevation potential. I always like to do this just to make sure that we haven't, dropped out a term or something. This is, if units check out, usually, you've got it, got everything. So let's just do that. The units of unit weight is mass squared, length squared, volume is a length cubed, and z is a length. So that goes with that, and those are the units of energy. So we're good. Okay. So kinetic energy. So we've got our volume, and it's moving with call the moving with the velocity. I'll do velocity as lowercase v, and I'll put a little thing on there so that it doesn't look like volume. Okay, so the kinetic energy of a block. Move along, remember this from physics. What it is. Kinetic energy.
Half mv squared.
Yeah, so it's just 1/2 mv squared. Right? Okay. So let's go and use the density here so we can get a volume. So we have mass, so that would be volume divided by density. Okay. So remember last time we had unit weight in here as rho g. I'm gonna that's not right. So the other way around, right? Density is, that's right. Right? Mass per volume. Right. No, I'll get it. I'll get it. Rho v. How about that? Yeah. So density is mass per volume. So volume is rho. No. Using mass. There we go. Okay. So what I want to do is get it in terms of the unit weight again. So I'm going to multiply top and bottom by g. And then I can write this like this. That's unit weight. Okay. That looks right, but we should check it. So let's check the units. The unit weight we said was mass, T squared, L squared. G is. Okay. So there's unit weight. G is length per time squared, volume is length cubed, length squared per time squared. Okay. So there's that. And there's that. That goes with that. So no, mass doesn't cancel. So mass length squared times. The unit should be good. Okay. That unit. All right, so pressure, energy. So pressure is acting on this cube in all directions. The energy from that is just going to be the pressure itself times the volume. So pressure is the force per area. And force is mass times acceleration. And we go and divide by squared. So mass. Okay, so there are the basic units of pressure. So the pressure energy is going to be that. This will be the basic units. Times the volume, which is length cubed. So that mass length squared piece. Another unit check. Okay, so those are the different terms. We've got them checked out. And we're gonna add them together to get the total energy on that cube there. Okay, so add them all together. So E was. So what do you got from your notes? The elevation energy. Anybody just let me know.
Yeah, easy.
Gamma.
Volume, elevation.
Volume. Z. Okay. Let's just do this as energy total. And then the kinetic energy that we got at the end has gamma in it. Gamma
Over 2G.
over 2G. And there's a V in there.
Volume. Velocity squared.
And a velocity squared. Okay. Good. And then the last one was PV, right? Okay. So that's the total energy in that cube. And so what we said originally was that flow is going to go from high energy to low energy. So it's going to go from high this to low this. Okay, so one problem is going to be that when we set this up conceptually, it was useful to do this based on just a volume of water, unit volume of water. But if we have a big thing of water that's flowing, what's that unit, right? So we don't really have like a chunk of water. That's not a useful concept for describing flow going from high to low energy. So we can modify this though in a simple way. And we can say this is the total energy, but if we wanted to apply it to a large body, we can say we'll go with the energy density. So the energy per unit volume. And so we just do that by dividing through by volume. So, and we have volumes in all of these terms, so this is just going to cancel out the volumes. Okay, so energy density, this is now something that can be variable within a body of water. And we can have flow going from high energy density to low energy density. That fact is what drives flow. And have flow going upwards or downward or sideways, whatever. Flow is going from high energy density to low energy density. Okay, so that satisfies our conceptualization about how flow is going to work. For hydraulic problems, we can make life simpler. The units here, the units of this is energy density, right? And so we said the units of energy was mass, length squared, time squared. So if it's per volume, there's length cubed. So the units of this would be mass per length times squared. Okay, so we can do that. That's no problem, but it ends up being a little cumbersome. What we do to make life easier is we go and we're going to normalize everything by the unit weight. So we're going to normalize the energy density by the unit weight. And we have 2 unit weights here that are just going to cancel. And then the unit weight shows up there.
Just a clarification.
Okay.
Capital P is pressure, right?
Pressure, yeah.
Okay.
Yeah. So the energy density per unit weight, we'll call that the total hydraulic head. Okay, so that's that. And here's the term. And there's V squared over 2G. And then P over gamma. Okay. So this is the total hydraulic head, and it has 3 components: the elevation head, the velocity head, and the pressure head. And we started saying that it flows from high energy to low energy. This is the normalized energy density. So we're going to say flow goes from high hydraulic head to low hydraulic head. Okay. So I'm going to rewrite this total hydraulic head. Okay, has these three components. Now, what I want to do is take a look at this. This is the velocity head from the kinetic energy. And I want to look at it for two cases, for the flow in a stream and the flow in groundwater. Okay, so the flow of the stream, if you went out the 18-mile creek, we go out there and we have a class out there and we measure the velocity. And it moves along like this, something like that. You know, so it's a foot, 2 feet, so a second. So what I'm going to assume, though, just to make life easier for calculations, is that it's going at a meter per second. A little bit faster than actually here, but maybe we go to a little faster part of the stream. So the velocity head, let's just do this for a stream. So velocity head stream, if the velocity is 1 meter per second, we've got 1 meter squared per second squared. 2g. So g is what, 9.81 meters per second squared. So I don't want to get out a calculator. So I'm just going to say, well, it's close enough to 10 meters per second squared. Okay, so I can go then 2 and 10 meters per second squared. So that would be 1/10, it's half of that. So it's 0.05. And the second squareds go, the meters go, so it's meters. Okay, so the velocity head is 0.05 meters. So 5 centimeters, like that. And we see here actually an important aspect about hydraulic head. So remember on the previous slide, we said this was energy density. Well, what we've done by normalizing by the unit weight was to get these into units of length, meters here. Okay, so that's really going to be nice because it'll give us something we can visualize. It's easy to visualize lengths, and so we'll be able to draw it on the board. So we've got the hydraulic head, velocity head in the stream, something like this. But in groundwater, the flow is slower. So instead of a meter in a second, it's about a meter in a day. Depends where you are, but let's just say that's the ballpark. So the velocity head in groundwater, where it's a lot slower, is going to be 1 meter squared per day squared. Divided by 2. Squared. Okay. So now though we have to convert this. This is a day squared and a second squared. So in order to get this to work, we've got to do the conversion. So how many seconds in a day? So there's this many seconds in a day. So let's call it 100,000. It's 86,000. Let's call it 1 day. Okay. So one day squared is about 10 to the 5th squared seconds. Okay, now the units cancel. And I have units of meters. Okay, so let's go and figure what this is. So there's there's 10. We'll do the 2 later, but there's 10, and here's 10 to the 5th squared. So that's 10 to the 10th, right? Do that, multiply by 10, 10 to the 11th. And down the denominator, so this is gonna be, so if you just take that, 10 to the 11th, and bring it up, it's 10 to the minus 11. So this is 1/2 times 10 to the minus 11 meters is the velocity head. So you have a feel for that, how big that is? Like this. 10 to the minus 11, have a feel? No? So, potassium ion is about 10 to the minus 10 meters. So this is smaller than, smaller than some atoms. I think this is like subatomic scale. So what it means is that in groundwater, we just often are going to set that equal to 0. So for groundwater, we can say that the total hydraulic head is just the elevation head plus the pressure head. And that will allow us to calculate what the hydraulic head is and how it's distributed between pressure head and elevation. I think that would be a good place to stop. We can pick it up next.